Good afternoon, everyone. Today we have a great pleasure to attend to the talk by the department chair, Professor Chaitanya Swamy. And I guess there is not much introduction needed. Chaitanya did graduate studies at Cornell under the supervision of David Schmois, and then after short postdoc at Caltech, Chaitanya joined the department here at Zendo. And today we will listen to the talk about stochastic minimum norm in combinatorial optimization. Thanks.
Okay. Thank you. Thanks, Kostya. Thanks for everyone for being here. I'm going to be talking about stochastic minimum norm combinatorial optimization. This is joint work with my former PhD student, Sharat Ibrahimpur, who's also in the audience. Yeah, there. He didn't come here to listen to this talk. He came because he was convocating. So this talk is about optimization in the face of uncertainty. So let me start by talking about optimization under uncertainty. So why are we looking at this? Because, well, I mean, uncertainty does turn out to be an unavoidable aspect of various decision environments. So for instance, exact data may be unavailable because of how it's generated or measured or captured, or it may be expensive to obtain. And so we need some models to deal with optimization or decision making in the face of uncertainty. And one popular framework is stochastic optimization. So this is really a metronym for a whole class of models. But the commonality across this class of models is that the uncertainty is captured or represented by a probability distribution. So whatever uncertain data there is, we are going to think of that as random variables given by a distribution. And this has lots and lots of applications in scheduling, telecommunication networks, transportation, et cetera, et cetera. And actually, this stochastic optimization, one particular model in stochastic optimization was proposed way back by Danzig in the 1950s. So to set the stage for what the class of problems that we're going to talk about, let me collect some features of various stochastic optimization problems. So something that's common across various stochastic optimization problems is that the costs are governed by some random variables, and in many cases you have to take decisions given only sort of distributional information about those random variables, right? And then so each solution induces a random cost vector, and you want to choose this, and then there's some objective function that aggregates the entries of this cost vector, and we may want to minimize the expected cost, the expected value of that objective function. And some common objectives are like L infinity norms. So if you're in a scheduling problem or load balancing, then L infinity norm can sort of capture the maximum machine load. So that's called the make span. L1 norm corresponds to a min-sum problem. So for instance, there's the k-median clustering problem where you want to minimize the sum of distances of costs are given by the distances of points to the nearest center, and the clustering cost is the k-median cost. And often these two objectives tend to skew solutions in different directions. So people look at LP norms as a way of interpolating between these two extremes, right? And again, I'm not saying that sort of every stochastic optimization problem falls into this setup. In particular, I mean, there are lots and lots of models where we can make decisions adaptively, right? So you can sort of, you make some decisions, realize get to know the realizations of some random variables, and then you can make more decisions, right? That's an adaptive model. But often non-adaptive solutions are, well, they're definitely easier to describe and implement. So that's one reason why one may want to focus on non-adaptive settings or non-adaptive solutions and see, well, what can we do with that, right? So now to talk about stochastic minimum norm optimization, I'm going to change this objective here to let it be some arbitrary monotone symmetric norm, right? Okay, so I'm not going to define, or not define on the slide what a norm is, but we all know what a norm is. It's a homogeneous function, maps 0 to 0, and satisfies the triangle inequality. But let me define what monotone and symmetric mean. So monotone is what you would think it means that so for non-negative vectors, if I'm increasing the coordinates, the norm does not decrease, right? And in this talk, I'm only going to be focused on non-negative vectors. So I'm going to be a bit sloppy in terms of some definitions because they're just going to be talking about non-negative vectors, right? And symmetric means that if I permute the coordinates, then the value does not change, right? So, and some notation that I'll use is I'll use this notation x with a down arrow to mean x with its coordinates sorted in decreasing order. So symmetric means that the value of the norm is the same as the value of this fixed permutation of the coordinates. Okay, so let's look at a couple of concrete problems in this setup. So one is load balancing. So here I have a bunch of machines, unrelated machines, and stochastic jobs. So each job, its processing time on a machine is given by a random variable, xij. These xijs across for a given job, I mean, unrelated means that these xijs could be different for different i's, right? It's not necessarily that the job has the same processing time across all machines. That's called identical machines. That's why this is called unrelated machines. And we'll assume that different jobs are independent. So if the job is different, then these two variables are independent. But for a given job, the xijs across different i's could be arbitrarily correlated. And then I'm given a monotone symmetric norm, which is over vectors in Rm. M is the number of machines. A solution is an assignment of jobs to machines. And once I have the solution, I can look at this cost vector, which is the load vector on the machines, sum of processing times of the jobs assigned to that machine. And my goal is to minimize the expected norm of that load vector. Okay, so this is minimum norm stochastic load balancing. Any questions about the definition? Sorry? Minimize with respect to assignment. So I want to choose an assignment that minimizes this. Okay, good, thanks. We talk about another problem, fairly fundamental problem. So spanning tree, right? So I give you an undirected graph. The edge weights are random variables. I give you a symmetric norm on Rn minus 1 because there are n minus 1 edges in a spanning tree. So the solution is a spanning tree. Once I have a spanning tree, I can look at this cost vector found by the cost of the edges included in that spanning tree, and I want to minimize the expected norm of that. Okay? So these are two problems in this framework of stochastic minimum norm combinatorial optimization. Let me say a bit about why we are looking at it at this level of generality of monotone symmetric norms. So first of all, because it's so general, it's a very rich class of objectives. It captures all LP norms. And also it captures some norms that are sort of quite different from LP norms in a certain setting, in a certain way. So there's this class of norms called top L norms, where I sum up the L largest coordinates, or L largest coordinates in absolute value again, because I'm just talking about non-negative vectors, I'm just going to say coordinates, right? And this turns out to be a sort of a very nice and fundamental class of monotone symmetric norms, and we'll get to why it's fundamental. And if you think about it, right, so I said LP norms are usually considered because there are means of interpolating between these two extremes of min sum and min max, but the same you can do with top L norms, right? Top 1 is min max, and top n is min sum. And this is a sort of a polyhedral way of doing it, right? The unit ball of this norm is a polytope. As opposed to a general convex set or a ball for the other norms, right? So by looking at these monotone symmetric norms, we get a versatile model. It's a vast generalization of LP norms, and the hope is that if we can get positive results here, then it gives us a unified way of looking at norm-based objectives. Okay, that's really the goal. But then there's sort of another subtle reason for studying this, which is that these norms are closed under various operations, and that gives them a great deal of modeling power. So if I take a non-negative combination of monotone symmetric norms, I get a monotone symmetric norm. If I look at the max of a bunch of monotone symmetric norms, I get another monotone symmetric norm. And this is quite nice because, for instance, this, so let me illustrate why this can sort of give you a surprising amount of modeling power. So suppose in my problem, instead of sort of minimizing one norm, I had a bunch of budget constraints for different norms. So these FRs are different monotone symmetric norms, and I wanted a solution whose cost vector satisfied that property, right? Let's say this is a deterministic problem for now. So this is completely equivalent to saying that the maximum of this ratio is at most 1. But now, because of the closure properties, this quantity is itself a monotone symmetric norm. So I can model all of these multiple budget constraints by saying that I want to minimize gx, or just decide if g of x is less than or equal to 1. So this is kind of a nice illustration why sort of this, you do get a whole bunch of modeling power. So by having these multiple budget constraints, you can get fine-grained control over your cost vector, which is often useful in stochastic settings. And hopefully I'll be able to get to this, that if you look at random variables that are given by Poisson distributions, this modeling power turns out to be quite useful. Okay, so if you think about stochastic minimum non-combinatorial optimization, there are really sort of 3 sources of difficulty for this problem. Right? So one is the underlying combinatorial optimization problem, how difficult that is. So I mean, you would expect that load balancing is probably more difficult than spanning tree, because spanning tree is quite easy, at least in the deterministic setting. Then, because you have random variables and they could have arbitrary distributions, so the stochasticity gives you another source of complexity. And the third thing is that, well, we're looking at this sort of very general object, an arbitrary monotone symmetric norm. Right? So how do we reason about just an arbitrary monotone symmetric norm? I mean, L1, LP, et cetera, even top L, we have some definition, and we can sort of work with that. Right? So let me talk about what we do. So we give a framework for tackling stochastic minimum norm optimization problems, and that's got sort of 2 components. So first, we show that the generality of monotone symmetric norms can be simplified, and you can work with just these top L norms. So if you wanted to control the expected norm, whatever that f is, it's enough to control the expected top L norms. Right? So bounding that can be, with a constant loss of approximation, translated to bounding the expected top L norms. Right? And top L, again, it seems like an easier object to deal with, but even there, we have to sort of think about how to deal with it, because unlike L1 or L2 or LP to the P, these norms are not separable. Right? So even top 1, which is the expected max, that's not usually an easy object to reason about. Right? So then we give some techniques to handle the expectation of top L norms, and when we combine these two, that's sort of really the more problem-independent way of looking at stochastic minimum norm optimization. And then for load balancing and minimum spanning tree, we apply this framework to obtain approximation algorithms for these problems. Right? So this step is, of course, problem-dependent. Here, as we'll see, we can get sort of stronger results for one problem and not quite as strong results for another problem. Right? And as you may expect, spanning tree is easier, so we get stronger results there, and somewhat weaker results for load balancing. Okay? So now, before I go further, just to make sure we're on the same page, because I use this term approximation algorithm, let me sort of quickly sort of say what that is. So these problems that we are looking at and kind of optimization problems in general often turn out to be intractable. So we often cannot hope to solve the problem efficiently, i.e. in polynomial time and exactly. So we try to devise what's called an approximation algorithm that always runs in polynomial time and returns a solution. So for a minimization problem, it always returns a solution whose cost is within alpha times the optimum. Right? So it has a goodness guarantee, just not exactness. It is polynomial time and has this quality guarantee. And this factor alpha, this number alpha, is called the approximation ratio. Okay, so now let me delve a bit more into the contributions. So for stochastic minimum norm spanning tree, we get a constant factor approximation. For stochastic minimum norm load balancing, we have more of a sort of spread in what we know how to do. So if I look at general distributions but top L norms, specifically just top L norms, we can get a constant factor. If I look at arbitrary monotone symmetric norms, but the special case of Bernoulli distributions, or weighted Bernoulli distributions, so a job has Xij is 0 with some probability and some value Pj with Pij with some probability. For that, we can also get a constant factor. this is the most general setting. And here we don't quite know how to get a constant factor. We get this maybe morally a constant factor, okay? Log by log m approximation. And yeah, so this is indeed an open question, whether you can improve that. I mean, that sort of, that when you see that kind of factor, you often suspect that there should be a cleverer order 1 approximation. And that's also the hope, but we don't know how to get there. Right? Yes?
So for the spanning tree problem, the weights on the edges are random variables.
Yeah.
And like in the case of, for example, weighted Bernoulli, they would all have the same distribution?
No, they could be different Bernoulli distributions.
I see. But you get a order 1 approximation ratio for any distribution family from this class or something?
Yeah, so if every xij is a weighted Bernoulli random variable, and we know that, I mean, so the distributions are given to us in the input. If they're weighted Bernoulli, then you get a constant factor. Right. Yeah. Good, thanks. Yeah?
Do you know any separation, I mean, a hardness result between the two columns? So there's some problem where a hardness result where the monotone symmetric is actually strictly separated from.
I don't know of a hardness result, but I do know sort of limitations in the state of the art, even for in the deterministic setting. So I do know of problems for which, even in the deterministic setting, you can get a constant here, but you only have something like polylog or polylog in the deterministic setting. But yeah, I don't know of any hardness. Yeah. Okay. Good. Thanks. So yeah, one of the reasons why we looked at weighted Bernoulli is because in some prior work, that turned out to be sort of the main case, and there was actually a reduction to the weighted Bernoulli setting. But here, at least right now, it seems easier than the general setting. We also looked at identical machines. So again, this is a setting where you get you have the same job size, although that's random. And we don't know better guarantees in this case, but the guarantee is a bit stronger, or it's stronger in the sense that we get an assignment such that no matter what monotone symmetric norm you pick, it is within that approximation factor for that monotone symmetric norm. So this is, I mean, the first time we see it, this is a bit surprising that, okay, there's one solution that's good for all monotone symmetric norms, but also in other settings, this kind of thing often happens for identical machines. We looked at also the special case of Poisson distributions, and here the approximations are much better. So this is a 2 plus epsilon, and for identical, they become 1 plus epsilon for any positive epsilon. And that uses, that doesn't really fall into the framework that I mentioned earlier, so that actually follows from a clever reduction to the deterministic setting, and hopefully I'll get to that, yeah.
For simultaneous approximation, are you assuming some scale? Because you can have, like, you can scale the norms, right?
Yeah, but I mean, so scaling a norm does not change the quality of the solution, right? The optimum will also scale. Yeah. It is important, though, that it's norms, because norms are homogeneous. Like if you have some steeply increasing convex function, then yeah, you can easily encode NP-hard problems. Good. And just a sort of a quick shout out to previous work. So prior work looked at these LP norms. So Gupta et al. Gave a constant factor for the L infinity norm, or top one, and there was much before that in 2000, or that's the journal version of the paper. Kleinberg, Rabbani, and Tardosh actually developed much of the machinery. They looked at identical machines and they gave a constant factor. Again, for the L infinity norm, which is usually called the make-span objective, and Molinaro gave a constant factor for general LP norms. The Poisson setting has also been studied, but again, just for the L infinity setting. Sorry, the L infinity setting, or the top one norm, where there's and identical machines where there's a 1 plus epsilon that was known. Okay, so what I want to talk about is this sort of more problem. I want to really delve a bit more into the problem independent aspect of this contribution, which is how do we deal with the expectation of an arbitrary monotone symmetric norm, because I think there's sort of nice ideas in there, and it's a cute result. So yeah, so how can we handle an arbitrary monotone symmetric norm? Let me introduce one other definition. So an ordered norm is just a non-negative combination of topple norms. And if you think about it equivalently, you can think about it as there's a decreasing weight vector or non-increasing weight vector, and you're looking at the WL times the Lth largest coordinate, and you're adding them up, right? That's completely equivalent way of stating things. So in some prior work with Deeparnab Chakravarti, who was a long time back, a postdoc here, we looked at deterministic minimum norm optimization problems, and we proved the following structural result, which states that if I give you a monotone symmetric norm, then there is always a way of kind of writing it as the maximum of a collection of ordered norms. Right? So there's a collection that I can find, and f of x, I mean for non-negative x, can be written as the maximum of the ordered norms that are over that collection C. So another way of thinking about this is that, well, as I mentioned, these norms are closed under various closure properties, right? Non-negative combination and max. So in principle, you could think about, okay, so this is a non-negative combination of topple norms. I can take a max. I can keep doing this. But what this is saying is that only one round is enough. Just one round of taking a linear combination, non-negative combination, and then a max. Every norm, every monotone symmetric norm can be expressed like this. Right? And in that paper, we also showed that we can make this collection polynomial size, which was important in the context of that paper. But what this tells us, what's going to be more important for us, is that this implies that if you have two vectors, y and z, and the topple norms, all the topple norms of y are bounded by alpha times the topple norms of z, then you can take any norm and you'll get this inequality. The norm of y is at most alpha times the norm of z. Just because, I mean, this is just linear in all the topple norms, right? And to get this, we don't really need this structural result. So this is actually implied by this majorization theory of Hardy, Littlewood, and Polya. But the structural result will play a role in how I'm going to sort of think about the expected value of a norm. So in the deterministic setting, right, this gives us a lot of power because this tells us that if I wanted to get an alpha approximation guarantee, it suffices to find a solution whose cost vector y has this property with respect to the cost vector of an optimal solution, z star, right? And that is really sort of the approach that's taken in this prior work on deterministic minimum norm optimization, and there we use this to get a constant factor for the deterministic minimum norm load balancing and the minimum norm version of K clustering. Right? So now, yes, question?
So for the theorem, if I think of the norm as a convex body,
yeah.
I will just approximate convex body to the point of.
Well, it's an exact approximation. So the way we prove this is that, so this convex body or this norm, you can look at its subgradients, and those actually define these weights. So if you look at the subgradient, so for instance, L2 norm, right? The L2 norm of x can be written as the max of all the dot product of all unit vectors with x. And you can think of unit vectors with sorted coordinates. So that's kind of what's happening here. That's how we got this, right? Okay, good. So this tells us, this gives us at least some handle on a monotone symmetric norm. So now let's try to use this. So now I want to handle the expectation of that. So again, f can be written as this max of this W transpose x down. So a natural question that arises, so okay, I want to reason about this. I can replace that f by this thing here. And can I kind of interchange the max and the expectation, losing only a constant factor? All right. Now, this may seem like a crazy thing to think about, right? I mean, usually interchanging the max and the expectation, I mean, you would lose a lot, right? But the reason we are looking at this is because this has a nice interpretation. This, I can take the expectation inside because this is just a linearity of expectations. And this quantity is then just the norm of this expected sorted y vector, right? So this packs in a bit of notation. So let me sort of clarify what this means. So here, I'm looking at this random vector y and sorting its coordinates. So the first coordinate is the maximum. The second is the second maximum. And what are the expectations of this vector? So the first coordinate of this expected vector is the expected maximum. The second is the expected second maximum, and so on. So the sum of the first L coordinates would just be the expected top L norm, the sum of the expected max, expected second max, and so on, right? So the question is whether the expectation of the norm is within some constant factor of the norm of this expected sorted Y vector. Again, I mean, if it's not clear why I'm looking at this question, here is maybe a more intuitive way of asking the same question. So on the previous slide, I showed you this thing that if the top L of Y for a deterministic vector, if top L of Y is at most alpha times top L of Z, then the norm of Y is at most alpha times the norm of Z. I can try to ask the same question for the expectation. So if I have two random vectors whose coordinates are independent, and if the expected top L norms of Y are at most the expected top L norms of Z, I can put in an alpha in there because things are always homogeneous. Then is it the case that the expected norm of Y is at most some constant factor times the expected norm of Z? Right? This is completely the analog of this, the top L Y at most top L Z means that norm of Y is at most norm of Z. Right? So, and it turns out that these two questions are equivalent. Right? So the same, sorry, the punchline is that we do prove this. These two constant factors are the same, and because these two turn out to be equivalent questions, and what we show is that, well, so we don't know what's the best constant factor there that's possible, right? So in the archive version of this paper, I mean this factor has been improving, although we haven't worked on it for a while, so it's stagnated at what Sharad proved in his thesis. But we proved a factor of 28 in the archive version. Sharad gave a different proof in his thesis, which made it around 7.7. And it is an open question, and it's sort of a completely mathematical question. It's not an algorithmic question. Like, if you have these two vectors with independent coordinates, what's the best factor that you can say for the expected norm of for this thing here? I think that's sort of a very appealing question. So there is a lower bound that shows that you can't get 1. I mean, you would expect that. So Sharad had a lower bound of about 1.2. I was doing some computational experiments, and I could sort of push this to 1.3. But I don't know whether you can get 2 there, right? So I mean, like some nice small constant there. Right? So I want to sort of show a bit about how we prove this, right? So the theorem that we want to show is that if I have a random vector Y whose coordinates are independent random variables, it doesn't matter what those distributions are, right? The only constraint is that they are independent random variables. Then the expected norm of Y is within a constant factor of the norm of this expected sorted vector, right? This is the statement that I want to sketch a proof of, okay? Okay, so let's look at this quantity, which is the histogram of Y. So n greater than theta Y is the number of yi's that are greater than theta, right? And because f is a symmetric function, f of I is just going to depend on this histogram, right? Because this histogram tells me exactly what are the coordinates of Y. I don't know the ordering of them, but I know their values, right? This is the largest value, this is the largest value, this is the second largest, and so on. So I know all the coordinates of Y from this histogram. Okay, so f just depends on the values of the coordinates, not on the order, because it's symmetric. So everything about f is completely determined by this histogram, right? And so now let's ask what would be the top L norm of Y. And the top L norm of Y, I can sort of describe it very easily in terms of this picture. Namely, let me take a Y-intercept of L and look at the sum of all of these entries, right? That is exactly the top L norm, because this is the largest, this is the second largest, and I'm going all the way up to the Lth largest, right? So that area is precisely the top L norm of Y. So that's a sort of nice visual representation of this top L norm. So now I'm looking at this random variable, so let me look at sort of this expected histogram curve. So let's look at the expectation of this quantity, the expected number of coordinates that are greater than theta. And something very nice happens that, again, if you look at this L-intercept, if you draw a line at y equal to L, and you look at the analogous area of this expected histogram curve, then that nicely corresponds to the expected top L norm of y. Right? This requires a proof, and sort of the more precise thing is that this is at least the expected top L norm and at most twice that. Right? So we get this nice relationship that the expected histogram curve determines the expected top L norm of y. And so now let's look at this vector here. So I know that the norm is just determined by the top L norms, or whatever I have inside. And the top L norm of this expected sorted y vector is just the expected top L norm. Right? I'm adding the first coordinate, which is the expected max, the second coordinate, which is the expected second max, and so on. So all of this norm is completely determined by the expected top L norms, which means that since the expected top L norm is determined by this expected histogram, this quantity is then also completely determined by this expected histogram. Okay, so that's sort of the upshot that I want to get at. So the f value is determined by the histogram, and the f of the expected sorted y vector is completely determined by this expected histogram curve. Okay, and once we have this, or really, and this was the main insight, then we can sort of finish up the proof using kind of standard ideas. So we want to talk about the expected norm of f using Chernoff bound. So if I have a realization of y, that gives me some green histogram curve. And we can ask, what is the probability that the green curve is above like alpha times the red curve, which is the expected histogram curve. And using sort of Chernoff bounds and union bound, you can show that decays exponentially with alpha. And when you have this exponential decay with alpha, you get the expectation statement. Right? So again, this is kind of the key insight, or the fact that the expected top L norm is given by this histogram. If I told you that, and I kind of locked you up in a room and said, okay, you can't get out until you prove this result, you'd probably prove it. Right? Some of you might be thinking, nice person we elected as chair. So let me get back on track. So that's basically the proof idea, right? So that's what shows this statement of expected norms. And for stochastic spanning tree, utilizing what we have here to get something from stochastic spanning tree is fairly direct. So again, so from what we know, if I wanted to get something whose expected norm is within some factor of the expected norm of the optimal solution, I know that I just have to care about expected top L norms. And I also know that these expected top L norms are sort of roughly these corresponding areas that we have for the two histograms. So I just need to worry about arguing or producing some solution where that expected area, that area is roughly the same as this area. Or roughly speaking, the histograms kind of match up, right? Now, how do we encode this? Well, we can kind of guess all of these tau star L quantities. And we can kind of say, like, showing that this is about this, we don't know what that tau L is, and that's sort of one problem that we want to solve. So we're going to just guess all of these, and we're going to say that the y coordinate of the expected histogram curve is roughly L for those guys. Right? So if I have this, then that is kind of saying that, okay, at all of these points, that red curve is roughly matching up with this blue curve. Right? Except there is one other thing. So it is matching up at all of these points, L equal to 1, 2, 4, 8, etc. But then there is a sort of portion of the curve that's beyond this tau star 1. And we also have to ensure that sort of this area and that area roughly match up. Right? But if we can do these two, then it's hopefully not surprising that like this is giving us a lot of control over that this red curve is roughly matching up with this blue curve, and this is telling us that the tail is also roughly the same. So if we have those two, then we can enforce this, and to encode this, you can write this, you can encode this as an LP, because this is counting the number of coordinates that are larger than tau star L. We know the distributions of these edges, so we can just write down a linear expression saying that the expected number of coordinates above tau star L is at most L. Right? This guessing step might sort of raise a red flag that they're kind of log n quantities we have to guess, but because these tau stars are actually decreasing, instead of that taking like n to the log n time, it actually can be done in polynomial time. Right? So all of this guessing can be done in polynomial time. We can write an LP, and then because of the property of the spanning tree polytope, there is this sort of nice rounding framework called iterative rounding that one can use to round the LP solution and get these properties. So that's the plan for stochastic spanning tree. Stochastic load balancing is a lot more complicated, and the main challenge is that unlike spanning tree, where we had the distribution of the random variable corresponding to an edge. If I give you a spanning tree, then you know what are the edges in there, and I know the distribution of that edge. Here, the load on a machine is a sum of job random variables. We have the distributions of the job random variables, but getting from that the distribution of the load vector coordinates, that's not an easy thing, right? So that makes it sort of difficult to apply what we just did for spanning tree, in particular to reason about this quantity. What is the probability that the sum of these random variables is corresponding to a machine is larger than some theta? So what we had to do is come up with a different way of handling the expected top L norm. And to give a flavor of that, so it turns out that for any random variable, you can sort of define kind of this exceptional portion, this portion above theta, which is x if it's above theta and 0 otherwise, and the portion below theta. And these portions of these random variables allow us to write a expression for the expected top L norm, which is separable over the coordinates. So what we show is that if you look at, for a suitable value of theta, which is this theta star, the expected top L norm is roughly given by this quantity here, which is clearly separable over the coordinates. Right? And this is what we end up using. So let's go back to what we wanted to do. So if I wanted to reason about expected top L norm, now I have a different way of reasoning about it by looking at the expectations of these exceptional portions of the random variable. But I still run into this challenge, right? Because I don't really have access to the distribution of yi, right? Again, that's the sum of independent random variables. So here we have to resort to some machinery. So it turns out that the hard case is when all the jobs are small, so small with respect to that threshold. And here, going back to Kleinberg, Rabbani, and Tardor, so they use some ideas from queuing theory to define a notion of effective job size. And they showed implicitly that this quantity is roughly proportional to the total effective job size. So once you sort of figure out how to use this machinery, you can then write down a constraint, again in an LP, that in terms of the effective job sizes. And rounding that is much more complicated because it's load balancing, so we don't quite get a constant for the general problem, but in those special cases of top L norms or Bernoulli distributions, weighted Bernoullis, we can get a constant factor. Okay. So lastly, let me sort of briefly talk about the Poisson setting, because this involves this is a cute reduction to the deterministic setting. So now I'm looking at the setting where these job sizes are Poisson random variables, right? So Poisson distribution is this distribution where the probability that the random variable takes on some non-negative integer r is given by that expression, right? So nice thing about Poisson jobs is that, or Poisson random variables, is that the sum of a bunch of Poisson random variables is also Poisson, right? So if I look at the load vector y, right, and corresponding to an assignment sigma, then yi is distributed according to this parameter, which is the sum of the lambdas for the jobs that are assigned to it, right? I'm going to call that big lambda I. Okay. And one thing we can show is that if I give you two vectors of which you should think of as the vectors of these parameters, gamma and gamma prime, with this property that the topple norms of y are within alpha of the the topple norms of gamma are within alpha of the topple norms of gamma prime, then if I look at these two expressions, so this is a shorthand for saying that I'm looking at a random vector whose coordinates are given by Poisson random variables with parameter gamma I. Right? So I'm looking at this random vector, looking at the expected F norm of that. And I'm looking at the same thing for gamma prime. And if I have this relationship between these parameter vectors gamma and gamma prime, then I get that the expected value of this norm is at most alpha times the expected value for the gamma prime norm, for the thing that's given by the gamma prime vector. So for alpha equal to 1, this was kind of shown in some previous work. For general alpha, you need to prove a homogeneity property, which is what we did. So given this, now the plan is that, okay, we can kind of, again, so I can look at the optimal assignment and I can consider the lambda vector that's given by the optimal assignment. This is called that lambda star. And so I need to find an assignment where the topple norms of the vector lambda associated with my assignment is within alpha of the topple norms of the vector associated with the optimal assignment, right? That's, if I have this, then I know, so my solution is going to be distributed as the Poisson of this vector. The optimal solution is going to be distributed as a Poisson of this vector. And so because of this theorem, I get this alpha approximation guarantee. Okay? So I want to find an assignment which has that property. But this is exactly a deterministic minimum non-load balancing problem, right? Because I have a bunch of budget constraints for the different norms, just topple norms. And by the sort of trick that I showed earlier, we can fold that into one norm. Right? And that's how we get this. That's how we, and for the deterministic minimum load balancing problem, you can get roughly a 2 approximation, 2 plus epsilon, right? And 1 plus epsilon for identical machines. Okay, so that's basically what I wanted to say. So let me end with some summary and some open questions. So I talked about this very versatile model called stochastic minimum norm optimization, and we gave a framework for dealing with these problems. One of the sort of two key components of that is that you can control the expected norm by just controlling the expected topple norms. So we call this approximate stochastic majorization, just as majorization is used in the deterministic setting. And then you can reason about this. We gave ways of reasoning about this using either the histogram machinery or this separable proxy function. And we use this to get guarantees for stochastic minimum load balancing in spanning tree. And I think these tools, especially sort of these problem-independent tools, should find other applications. Whenever you have if you have some application involving norms, not just LP norms, then I think this can be quite useful. A few open questions. So I think one of the, I guess, pressing open questions, algorithmic questions, is whether you can sort of take this ugly log by log and improve that to a constant. Right? I don't know that that's impossible. Like we don't have any lower bounds indicating that this may not be possible. Something that I'd mentioned earlier, that in this inequality, which is just a statement about sort of random variables, independent random variables and norms, what is the best constant you can get here? Right? And then you can sort of ask, well, are there other kinds of functions f, or maybe more general than monotone symmetric norms, and other kinds of distributions where you can have this kind of inequality? Right? For instance, if something works for independent random variables, often it works for negatively correlated random variables, but we don't know how to extend this to negative correlated random variables. Right? So you can call this, maybe you can sort of look at this as a notion of niceness for a norm and a distribution, and you can ask sort of what other norms or classes of norms and distributions have this niceness property. Right? I was looking at the setting where you had to make all decisions upfront, just given the distribution. But again, it makes a lot of sense to also think about adaptive policies where like you can you're assigning jobs and then you sort of get to know the realization of the jobs that you've assigned, and then you can base your next decision based on that, right? So those are adaptive policies. There is some work for the make-span problem, which is the L infinity norm, the maximum entry. But at this level of monotone symmetric norms, there is no work that's known about this. And more open-ended questions. So one sort of model that has gained popularity in stochastic optimization is this distributionally robust stochastic optimization paradigm, which says that, well, okay, so we don't really often know we can't really sort of fit an exact distribution for the data. Usually sort of you get some data and you're kind of looking at you sort of have a class of distributions that could explain that data. And so this model says that, okay, let's, instead of working with assuming you have the right distribution, you should hedge against the worst distribution from this class. So in this context, it could translate to you have a class of distributions. Maybe you know that the jobs are independent, but you want to minimize the worst case expectation with respect to distributions in this class. Right? That's, I think, a very interesting model. And that's all I have to say. Thank you.
Thanks a lot for the talk. It's questions and answers. Sorry, Vijay, could you please wait?
Yeah, so if I'm understanding correctly, this expectation of f versus f of expectation for L1, L infinity, they're equal.
Well, so yes, any top L norm, they're equal because they're exactly the same thing.
Uh-huh.
Right?
Oh, okay,
for
so
LP
just
norms,
to
they're
ask
not equal.
for LP norm, but then that'll also be equal,
Yeah.
I guess.
Okay.
Yeah, so
Yeah.
okay, yeah. Thanks.
Any other questions? Okay, sorry.
Does the constant depend on the dimension? Like if I look at y here,
No.
if I have only a single entry in y,
Yeah.
I could have the right-hand side to be 0, and I could have the left-hand side to be arbitrarily large.
So I think one key thing here is that you're sorting this y vector.
I have only one.
You have only one coordinate.
Yeah.
Well, so if you have only one coordinate, then no, it should really be the same thing. Yeah.
But I have expectation of y inside f. So expectation of y, I can make it 0.
Well, I mean, a norm with just one coordinate, if it's a monotone symmetric norm, it's really just that coordinate, right, or a scaling of that coordinate.
But the right-hand side can be 0. If I make the expectation of y 0, and then you apply a norm, you get 0.
Okay, so these coordinates are non-negative independent random variables.
Okay, they are non-negative.
Yeah.
Okay.
Any other questions?
Actually, sorry, to re-ask my question, are they equal for LP norm?
Sorry.
No, they're not equal, yeah.
So what's the worst case gap?
That I don't know. I mean, okay, so to be completely honest, okay, so I'm pretty sure they're not equal, though I don't have a proof for that. Like, basically, anytime it's sort of more general than just a combination of top L norms, I doubt that they're going to be equal, right? I mean, you can always come up with some distribution and which will make them unequal, but I don't know what's the gap.
Yeah, I vaguely remember maybe something about if let's say y is like absolute values of Gaussians, I think maybe they're very
But they're
close.
not absolute values of Gaussians, okay? Right.
Yeah, then I think they're like close within little order terms, so maybe 1 plus little of 1, but I don't know if there's any gap.
Okay. I'd be curious to know about that.
Yeah, thanks anyway, yeah.
Yeah, but I'm fairly sure it would not be 1. Yeah, it could be like, right, so that little of 1 depends on the dimension then. Yeah, okay. could be.
Any last question? I was wondering, like, when you speak about spanning trees, is it hard to go to just basis of matrices from spanning?
No, it's the same
It's the
thing.
same.
Yeah.
Okay, so let us maybe thank the speaker again. And